So at this point, we're done with differentiation for now. And so, of course, the next topic in our advanced calculus class is integration. So let's do integration rigorously. So here is the first thing we're going to need to define to start talking about the integrals. So let's start with a closed bounded interval, a to b. And we say that a partition of AB, it's a way of chopping this interval up into finitely many pieces. So we call this a finite set P that's a subset of AB such that A is the smallest element in P and B is the largest element in P. And because P is finite, it has necessarily a smallest and largest element. And so here is our number line. Here is our interval from A up to B, and then the points of P would be something like you have to have one here, and then you're allowed to have finitely many, but as many as you want, scattered around the middle. So notice our partition has 5 points, and it's chopping this interval up into 4 smaller intervals. Now, sometimes we say the partition is the smaller intervals. So the partition would be these 4 little pieces instead of the 5 blue points. That's how we describe a partition in graduate level analysis. But I think some of the definitions are going to be a lot cleaner if we think of the partition as being just these, as being the blue points. And once you know what the blue points are, you can figure out what the red intervals are. So another little bit of notation. We let P contain n plus 1 points, so it contains some number of points. We just let n be, n is the number of little intervals here, which means it's one less than the number of points, and we name them xj in order. So A is x naught is less than x1, less than x2, less than xn, n plus 1 including 0, xn is B, and P is the set of all the xj's. So here is our next definition. We've defined a partition, so now we're going to define a Darboux sum. Let's let f be a bounded function defined on a closed and bounded interval. And let's pick some partition as defined above. And then the upper and lower Darboux sums of f over the partition P, they're written like this. U of fp, this is the upper Darboux sum. This is the sum from j equals 1 to n. Then you take xj minus xj minus 1. So the first one is x1 minus x0, which you'll note is in fact defined. And then we write supremum of the following set, the set f of x, such that xj minus 1 less than or equal to x less than or equal to xj. And we define the lower Darboux sum in the same way, but now we've got an infimum of the same set, but now it's an infimum rather than a supremum. And this is the picture many of you have seen in your regular or calculus courses, but let's draw that. So there's our axes. Here is our interval from A up to B. Then we've got to have a function here. It doesn't have to be a continuous function, although I think I will go ahead and draw a continuous function. It will make the picture a little bit cleaner. And then what we do is we take our partition. Here's x naught, here's x1, x2, x3, and then x4. Then what we do is we're going to draw some vertical lines at each of our partition points. And then to take the lower sum, you take the lowest your function gets in any of these intervals. Then you take that height times that width, that gives you the area of this interval in this rectangle. Then you add up all the areas of all the rectangles, that gives you the lower sum. And the upper sum, very similar. You take the highest point in each of these little regions. Then your rectangles are going to be a little bit bigger because you've got some extra area on top. And that gives you your upper Darboux sum. And let's have a couple of examples of computing these. So here is our first example. Let's let f of x be c, where c is a constant. And then the upper sum of f over any partition, sum from j equals 1 to n, xj minus 1. Then the infimum of f is c, the supremum of f is c, so we get a c. And then we've got c times, I'm actually going to write them like this. Is x1 minus x naught, and then x2 minus x1, and then we keep going up until eventually we get xn minus 1, and then you're going to notice that the x1s are the x1s are canceling, and then the x2 would cancel with the x2, x3 minus x2 here. And then the x3 would cancel with something. Eventually, the xn would cancel, and we end up at the end of the day with just c times negative x naught plus xn is just c times b minus a. So that's the upper Darboux sum of a constant, and similarly, the infimum is c, so we again have c times b minus a. So in the case of constant functions, the upper and lower Darboux sums are the same. That's in fact the only time they're going to be the same. Another classic example is this function. Let's let f of x, this is a piecewise defined function. It's 1 if x is a rational, and 0 if x is an irrational. Then if xj minus 1 is less than xj, then there is a point q between a rational number between them, and an irrational number between them as well. So what that means is that the supremum of the set of all f of x, xj minus 1 less than or equal to x less than or equal to xj. By the way, some notation here, you sometimes write this as the supremum over the interval xj minus 1 xj. F, that's just the supremum of all the f of x, where x is in the set written down there. That supremum, well, f is never bigger than 1, but it is equal to 1 at one point. And the infimum, on the contrary, f is never less than 0, and it's 0 at least one point. So that's 0. So in this case, the upper Riemann sum of f over any partition is just the length of our interval, and the lower Riemann sum is just 0. So this is a case in which the upper Riemann sum and the lower Riemann sum are always quite far away from each other. They're far away by the length of your interval. Let's have one more example of upper and lower Riemann sums. These are sometimes called Riemann sums, sometimes called Darboux sums. I'm going to let f of x equal x, and we're going to see how we use the upper and lower Riemann sums to estimate the area under a curve. Now, of course, in this case, the curve is just a trapezoid. Here's A, here's B. Here's x, and then our upper and lower sums look like this. Lower sum upper sum now, I'm sure you all know the formula for the area of the trapezoid, but I want to show you how we can use Darboux sums to estimate areas, and I want to use f of x equals x as this example because Darboux sums get awfully complicated awfully fast. The actual computation is a huge pain for anything much more complicated than this. Usually if you want to actually compute a Darboux sum, you get the computer to do it for you. So in this case, upper sum of f with respect to p, sum from j equals 1 up to n, xj minus xj minus 1. Then the biggest that gets is xj, our function f gets is xj. And our lower sum same thing with an xj minus 1. And now notice that with our partition, the error we're getting these little triangles here are included in the upper sum. That's too much. These little triangles here are not included in lower sum, so the lower sum is too little. But notice that as we get it more and more of our partition, but notice that if we got smaller and smaller partitions, we'd have less and less error. For example, if we used a partition that was twice as good here, then these pieces we'd have a little bit less. We'd have less error, or we'd suddenly not be overcounting these little rectangles or these rectangles. So we can get a closer and closer estimate to the correct area by using smaller and smaller partitions. And let's see what that works in this particular case. So the algebraic trick to these particular sums, and I had to try a couple of things to see what worked, so don't worry too much about if you can't see why I would do this. Let's write that xj minus 1. We're going to write xj plus xj minus 1 over 2, and then we'll subtract from it xj minus xj minus 1 over 2. And if you if you do your algebra, you'll see that these are indeed equal to each other. And then I can break this up into two sums. Sum from j equals 1 to n, xj minus xj minus 1, xj plus xj minus 1, all over 2. And then we have to subtract off the sum xj minus xj minus 1 squared over 2. And then this first term we see we've got a difference of squares. We've got an xj squared minus an xj minus 1 squared all over 2. And then our leftover term is going to hang out to and then our first sum, it's just like with before. Our x1 squareds are going to cancel, our x2 squareds are going to cancel, so eventually we'll get an xn squared minus x naught squared over 2 minus our little error. And we remember what this is, b squared minus a squared over 2. This is, as it happens, is the area of a trapezoid. Then the upper sum, I'm not going to drag you through the algebra. This was the lower Darboux sum. The upper Darboux sum. Turns out you can do the same trick, except for this minus sign here, you make it a plus instead, and you end up with your formula for the area of a trapezoid plus, instead of minus, this sum. And notice that we've got some squareds going on here. So this error term that we're adding in the upper sum, subtracting in the lower sum, is positive. And now notice that our little error piece. Then we're going to replace one of the xj minus j minus 1s by a supremum, by the supremum of the xj minus 1s. Maybe I'd better or call that xk, because we're using xj for something else. So, and then we've got a telescoping sum again. So what we're getting at is that if you take a very fine partition, a partition where these different is the xk minus 1s are small, then we can force these whole error terms here, we can force them to be nice and small. And so we can force our upper sum to be b squared minus a squared over 2 plus a little bit more, our lower sum to be b squared minus a squared over 2 and a little bit less. So we can force the lower and upper Darboux sums to get closer and closer to each other, and also closer and closer to the area of a trapezoid formula that we know and love. So before we start proving propositions about Darboux sums, which we will, I want to have one more word under our belt. So let's let P and Q be two partitions of the interval from A to B. And then if P is a subset of Q, we call Q a refinement of P. And so, of course, that looks a bit like this. Here's our interval from A up to B. Then we're going to take our partition P, and then Q, if Q is a subset, that means we have to keep all of these points, and maybe we can maybe we throw in a few more. And notice that now all of our intervals are getting smaller. So every interval between points in Q, it's contained in one of the intervals between points in P. So that's why we call it a refinement. It's got more points. The intervals are all smaller. So now we're going to prove proposition 3.1.2 in your book. Your book breaks this up into 3 pieces. I think it needs to be more like 7 pieces, so this is going to have a lot of parts. So let's let f be a function defined on a closed bounded interval. It's a bounded function, so it's got a lower bound and an upper bound. Let's let the lower bound and upper bound be little m and capital M. So f is a function. Its domain is a closed bounded interval. Its range, it maps into the real numbers. So its range is a closed bounded interval. And let's let P, Q, and R, these are all partitions of our interval AB. Then we've got the following things are true. So first off, we've got that our lower bound M is less than or equal to the lower Darboux sum of F with respect to, let's say, the partition R. Here is our second one. The lower Darboux sum of F with respect to the partition R less than or equal to the upper Darboux sum of F with respect to the same partition. And then A3 is that upper sum can't be any bigger than the biggest value of F gets times B minus A. So your book writes this as one long chain of inequalities. We're going to prove them one at a time, which is why I've broken them up into 3 pieces. So next thing I want to point out is next 2 conditions are both conditions about refinements. So part B is that if Q is a refinement of P, then the lower Darboux sum of F with respect to P less than or equal to the lower Darboux sum of F with respect to Q. Then, and a very similar condition is true for upper Darboux sums. only now it's in the other order. Let's see. And once you've proven all the above stuff, you put it together. This is really the interesting one. The lower Darboux sum of F with respect to any partition P, it's always less than an upper sum with respect to any partition, even if it's a different partition. The lower sum with respect to P is less than the upper sum with respect to R. So this is more complicated than A2. And the last condition, which actually follows from B1, B2, and A2, but is sometimes useful to have written down, is that the upper sum minus the lower sum, that is positive. But for the refinement, the upper and lower sums are actually closer together than they are for the original one. This, of course, is true if Q is a refinement of P. So let's go ahead and prove this. So we'll start with parts. So we'll start with part A1. Then the lower sum of F with respect to P is let's go ahead and prove this through these first few. Let's call the partition P instead of R. Lower sum of F with respect to P, that's the sum from j equals 1 up to n. Xj minus xj minus 1, then the supremum over that interval. Sorry, not the supremum, the infimum. But the infimum over that interval, F is always bigger than little m. Little m is a lower bound, so it's certainly less than the greatest lower bound. So we're left with b minus a times our lower bound. This is, of course, our usual telescoping sum trick. And then part A3, I'll just note that is a similar proof. You write down the upper sum, the supremum, capital M, and you're done. A2 is a little bit more interesting. So let's write this out. Lower sum of F with respect to our partition P. Now, xj minus 1, that is always positive. So if I replace this infimum by something that's bigger than the infimum, then this inequality will be true. And anytime you have a non-empty set, the infimum is less than or equal to the supremum. We know there's at least 1 point between xj and xj minus 1. There's at least one x in there. The supremum is bigger than f of x. The infimum is less than or equal to f of x. So we can just use the fact that the supremum is bigger than the infimum to show that the lower sum is less than the upper sum. Now part B is where things really get tricky. mostly because the notation is very difficult. So let's let P be x naught up through xn, and Q is y naught up through ym. And let's remind ourselves what a partition looks like. So let's see, here is A, here is B, then we've got x naught, xn, got x1, x2, and so on. And then we've got a y naught, maybe y1 is here, y2, y3, y4, then ym. In this case, n is 3 and m is 5, but it could be lots of different things. So remember, a partition is we're just throwing in a few more points. Sorry, that Q is a refinement of P means that Q is just P with some extra points thrown in. So let's set up the notation. And as I said, this is the hard part of proving part B. So P is a subset of Q because Q is a refinement. So what that means is that if xj is in P, then xj is equal to yk for some yk in our refinement Q. Q might have some extra points, but it has every point in P. And now we are going to define k sub j by xj equals y sub k sub j. So k sub j is just the index. And then a couple of things to notice. First is that k sub 0, x sub 0, x naught is the left endpoint, is A, and y sub 0, y naught is also the left endpoint. So x naught equals y naught, so x0 is yk sub 0 is y0. And very similarly, xn is the right endpoint, ym is the right endpoint, so kn is m. And the last thing I want to point out is that this sequence of kj's is increasing. Since we write xj minus 1, that's equal to y sub k sub j minus 1. And that's strictly less than xj by how the xj's are defined. They're defined in order, which is also known as y sub k sub j. And so ykj is less than ykj minus 1 is less than ykj, and the y's are an increasing list. They're not a sequence because there's finitely many of them, but they're an increasing list. So a bigger index means further to the right. So now let's write out what we're trying to prove. the lower sum of f with respect to q. That's the sum from k equals 1 to m, yk minus yk minus 1, then the infimum over this closed interval of f. And then, so there is the k term, there's the k equals 1 term, the k equals 2 term, the k equals 3 term. So I'm going to point out that you can always break up a sum like this. We're going to start with, from k equals 1, that's k naught plus 1, because k naught is 0, and then we're going to sum up to k1. And then we add another term where we start at k1 plus 1, and we sum up to k2, summing the same things. And so on. All right, so now let's write this using summation convention. So this first thing I wrote down, we're going to call that the j equals 1 term. So we start from k equals k, j minus 1 plus 1. We go up to kj. Then we've got a yk minus yk minus 1. Then we've got an infimum. The things we're summing are exactly as usual, but now it's from j equals 1 to n. So if you plug in j equals 1, you get this first term up here. If you plug in j equals 2, you get this second term up here. Notice they're only changing by the indices of summation. All right, now here's the next thing to notice. It's that if kj minus 1 plus 1 is less than or equal to k, so kj minus 1 is less than or equal to k minus 1, which is less than k is less than or equal to kj. So that is, if k is in this thing, if we're one of the k's in this second integral, then we can write xj minus 1 is ykj minus 1. That's less than or equal to yk minus 1. And of course, and yk is less than or equal to ykj, which is xj. So this interval, yk minus 1, yk, that's a subset of xj minus 1, xj. So the infimum, that's the biggest number that's less than f for everywhere in this interval. Then if you take the infimum over the xj minus 1 xj interval, you're looking at more points here on the right, so that's going to pull the infimum down. So what we can put a less than or equals to here. So what can we write? We can write L of FQ. that's greater than or equal to sum from j equals 1 up to n, sum from k equals kj minus 1 plus 1 up to kj. Then there's a yk minus y, k minus 1. Then I'm going to put the infimum over xj minus 1 xj here. And then notice that part, the infimum part, doesn't depend on k anymore, so I'm going to move it out front. I can't move it out of the j sum, it depends on j, but I can move it out of the k sum. And then notice that our inner sum, our rightmost sum, is now a telescoping sum again. We're going to get cancellations. So we get sum from j equals 1 up to n. And then I can put yk sub j minus y sub k sub j minus 1 plus 1 and then minus 1. And then if we just remember what kj was, ykj is now xj, ykj minus 1 is xj minus 1. And then we recognize that as the lower Riemann sum of f over the partition P. And that's what we wanted to prove. Part B2 is a very similar argument. Or you can go through the similar argument and you'll prove that a supremum over a bigger set is bigger than the supremum over a smaller set. Or you can use the fact that the upper sum of f over a partition, it's negative the lower sum of negative f over that same partition. And then finally, I don't want to go into too much detail on that because I want to spend a minute on A4, and this video is already very long. Let's let Q be the union of P and R. P and R are both partitions of AB, so Q is also contained in AB. It's the union of two finite sets, so it's finite. It has the endpoints, and it's a superset of both Q and R, so it's a refinement of both Q and R. Then we have that the lower sum of f over P, that's less than or equal to the lower sum of f over Q, and that is by part B1, which is less than or equal to the upper sum of f over Q, and that is by a part A2, which is finally less than or equal to the upper sum of f over R, and that is part B2. And that completes the proofs of parts A and B, and I'll let you think about part C. It's it follows from parts B1 and B2 and some very straightforward algebra.